So today's lesson is going to be over a concept in chemistry we call titration. With the titration, the point of it is you have something that you know its concentration, and then you have something that you don't know its concentration, and we use the known to solve for different values of the unknown. With titrations, there's three different types of titrations. We have an acid-base titration, which is the most common. We have redox titration, which is oxidation reduction reaction, and we have a precipitation titration. In each of the titrations, you're going to use a piece of lab equipment called a burette. I have a picture on the screen of a burette. With the burette, it is this long glass tube, and the burette is a measuring device, and it is a very accurate and precise measuring device. So it has markings on it, and you use those markings whenever you're making these measurements. You don't have to use a graduated cylinder or anything else to measure the volume. The burette itself measures the volume. There's almost always a question on the AP exam of how to read a burette, and so that's something that you should be practicing in your AP classroom, either through lab experiences or by looking at pictures of a burette. And so be sure that you're comfortable with reading the volume on a burette. And in a burette, you're going to have what's called the titrant is in the burette, and then you have the analyte, which is down in your flask. Typically, we know the concentration of the thing in the flask. We don't know the concentration of the thing in the burette. And so we are trying to do an experiment to find when these substances become equivalent with their number of moles of each of their substances. So for an acid base, we're trying to get where in this Erlenmeyer flask, we have an equal number of our moles of our base and our moles of our acid. And that is what's going to cause a titration to reach its end point, is when we have an equal number of moles. So this is what it's talking about. We typically use these to figure out the main thing is a unknown concentration. So in chemistry, our most common type of concentration is going to be molarity. And so the equation for molarity is equal to moles over liters. It's typically moles of solute over liters of solution, but your moles over your liters. And we don't actually write molarity as moles over liters for the final unit. When we solve for molarity, we're going to solve it in a big M. The other thing with concentration is, let's say that I had a concentration of 1.0. Then another way that it can be written is I can use brackets. I can put 1.0 and a bracket on the outside. And we now know that because these are brackets, we read that as the concentration of, or the molarity of. And so you'll see it written in different ways. Most titrations, we're trying to figure out the unknown concentrations. So for example, if I am doing this experiment, if I have an acid in here and a base up here, I know the concentration down here. We're going to do the experiment to figure out what the concentration is of the base using calculations to work backwards to figure out what its concentration is. In a titration, when we hit that end point or the equivalent point, that's when we have a moles of our known is equal to our moles of our unknown. And we often add, for an acid-base reaction, we often add something called an indicator into the reaction, because the indicator is the only way that we can figure out what the actual endpoint is, because you can't see. If I have two clear substances, then I can't look at them and figure out what's happening in the substances if they both just remain clear. Now, in an oxidation reduction reaction, most of the time, we don't have to use an indicator because most of the time the ions are colored. So for example, I might be doing a redox reaction with copper and iron. Well, iron almost always makes a reddish or orangish colored ion, whereas copper is going to be a bluish color when it's in solution. And so the redox titrations, typically we don't need an indicator because everything, the ions we're using have their own color. And the precipitation reaction, we don't need to use a an indicator because in a precipitation reaction, we're trying to see the precipitate, and that's a visual thing we can see. But most acids and bases are clear, and we cannot see whenever they hit their equivalence point. And so we add in something called an indicator. And you're going to learn a lot more about indicators later on when we talk about acids and bases. We choose indicators based on the substances we're mixing, the acid and base we're mixing. So it's a little bit more complicated. We're not ready to talk about that. Just know that we often use indicators to see the color change. How we do these is a pretty simplistic set of steps, but I have so many students who mess these steps up because they want to try to take shortcuts. So I try to number it out. So when you're doing a titration problem, no matter if it's acid-base, redox, or precipitation, you need to balance the chemical equation. That's always step one. You need to identify the moles of your known substance. It'll always give you enough information to solve for your moles of your known. Then you're going to use stoichiometry to get to your moles of your unknown. And then, depending on the question, typically we're going to solve for molarity, but sometimes it might ask you for the volume of your unknown. So it just depends on the problem. We will be using basic stoichiometry. We will also be using molarity equations, and you have to be able to balance. Now, sometimes that balanced equation is just going to be your net ionic equation. We've already talked about net ionic equations. Sometimes that's going to be a net ionic equation because we don't really care about the spectator ions. We care about the things that are actually involved in the chemical reaction that are participating. So let's go ahead and do a couple practice problems. So this first practice problem says that we have potassium sorbate, and it gives you the chemical formula, and it gives you the molar mass, is commonly added to diet soft drinks as a preservative. It says a stock solution of your potassium sorbate of known concentration must be prepared. It says a student titrates 45 milliliters of the stock solution, which the stock solution is the potassium sorbate, with 1.25 molarity HCl. And then it tells you in letter A, write the net ionic equation for the reaction between C6H7O2 aqueous and HCl aqueous. So let's start with writing out that net ionic equation. I'm going to do that up at the top because I'm going to need the bottom to be able to work out my problems. For me, I start out always doing a net ionic equation by writing out all of the things that are involved in the chemical reaction. So I have KC6H7O2, and that is aqueous, plus HCl, that is also aqueous, yields. So we have to figure out what our products are in this reaction, and we have to know about what's happening up here in our reaction. It's going to be a double displacement. So my K is going to go bond with my Cl, and my H is going to go bond with the C6H7O2. So K is going to bond with Cl. Well, we've been talking about SNAP for our solubility rules. The P in SNAP is potassium, which is this ion. And so when it does the double displacement, remember in double displacement, the two outer things bond and the two inner things bond. So whenever K and Cl bond, K is a positive one, Cl is a negative one, so it'll just be KCl. It is going to be aqueous. Plus, H is going to bond with a C6H7O2. This also has a charge of a -1 because if K has no subscripts and there's not parentheses around this polyatomic ion, we don't have to know what the sorbate ion's charge is. We can always figure it out from working backwards. I do know potassium is always a +1. If there's no subscripts outside of this with the parentheses, and if there's not a subscript for K, then that means that this is also a -1. And we should know H is always a +1. So they're going to bond +1, -1. So then it becomes HC6H7O2. Now, this is something we're going to talk a lot more in depth about later in the year. There are things called strong acids and weak acids. Strong acids completely ionize in solution and will be aqueous. Weak acids do not, and they will be considered a liquid. So this is actually a weak acid. You really would not be able to answer this at this point of the year. Once we hit the acid-base chapter, then you'll be able to answer this on your own. So then from here, we need to be able to go through and break it down into the complete ionic equation and then write my net ionic equation. And so again, we're going to have, I'm going to leave out states of matter because I don't have a lot of room here. So I'm going to have K plus 1 plus C6H7O2 minus 1 plus H plus 1 plus Cl minus 1 yields. On the other side, I'm going to have to erase these things. I'm going to have my KCl, which is going to completely ionize. So I'm going to have K plus 1 plus Cl minus 1 plus this stays together because this is a liquid. And remember, in net ionic equations, you do not separate anything that is a pure solid, a pure liquid, or a pure gas. So we're going to leave that. And then I told you guys in the other video about net ionic equations, when you see two things that are exactly the same, we can mark them out. Those are our spectators. We don't care about them. So K is a spectator and Cl is a spectator. So my net ionic equation is going to just be C6H7O2. I am going to include states of matter now. This is a minus 1 plus H positive 1. It is also aqueous. Yields HC6H7O2. This one's going to be a liquid. It's already balanced. I don't have to do anything from there. So then, now that I have my balanced equation, I can go on to start doing some math stuff. So one thing that you're going to have to get pretty comfortable with is converting between milliliters and liters. That is going to be a pretty common thing that you have to do. Almost all of our molarity questions is going to give it to us in milliliters, and we have to convert over. And so you want to be sure that you are confident in the way that you do that. AP does not actually give this to you in a clear way. They just tell you what factor of change it would be, the places that it would change. And so if you want to use this with stoichiometry, then in 1 liter, there are 1,000 milliliters. On the reference sheet, it just says that milliliters are 10 to the negative third, meaning that they are smaller than your liters. So in these problems, it's asking me to, it says a total of 29.95 milliliters of 1.25 molarity HCl is required to reach the equivalence point. Calculate the concentration, when we read those brackets as concentration, of K6H7O2 in the stock solution. And up here, it was talking about the stock solution. So if I go back to my previous slide, it says first, balance the chemical equation. Next, identify the number of moles of the known standard solution. So I have to figure out my known and the number of moles. So right now, this is what I have. I have 1.25 molarity of HCl. And I know that I've used 29.95 milliliters of my HCl. And so most of you should be pretty comfortable in setting up any problem for molarity. So there's lots of ways that you can do this problem. I'm going to show you 2 different ways. So if I'm going to just start with that 29.95, I'm going to convert using the 1,000 milliliters because milliliters has to cancel in 1 liter. And then once I get to that, then the molarity is equal to moles over liters. And so I can write this as 1.25 moles over 1 liter. And at this point, I really do need to include what my substance is so that I don't get confused as I'm doing my problems. I take the 29.95, divide by 1,000, and then multiply by the 1.25. When I work that out, that is going to give me 0.03, if I could write, 3744, and this is going to be moles of HCl. Okay, that is one option on how to solve this out. That would be showing how to do your conversion for your milliliters to liters. It would also be converting. So at this point, I've canceled milliliters, liters, liters, and I'm just left with moles. Okay, that's option one that you can use to solve these types of problems. Let me show you guys option two. Option two is going to be more of a shortcut method, and it's going to be doing some of the stuff in your calculator. So it depends on if you like to show all of it or if you want to do some in the calculator. So I'm going to start with 1.25 molarity is equal to moles, because I'm using this equation. So I plugged in my 1.25 molarity. I'm solving for moles, and I need liters. So in my calculator, I'm going to do the 29.95 divided by 1,000, because to get from milliliters to liters, you always divide by 1,000. And so I end up with 0.02995 liters. Then mathematically, I'm going to multiply both sides by the 0.02995 to isolate it, the variable, and cancel this off the bottom. So I do 0.02995 liters, and then times 0.02995 liters on this side. That would cancel all of it from here. So then whenever I work it out, I'm going to do the 0.02995 times 1.25. When you're multiplying or dividing, you round your sig figs based on whichever number in your calculations had the least number of sig figs. This has 3 sig figs. This has 4. So I'm going to round it to 3 sig figs. So it ends up being 0.0374. And then that's where it's going to end. So I just have 1, 2, 3 sig figs, and that is going to be moles, again, of HCl. So that is option number 2 of how to calculate this out. Now on the last one, it was rounded to 4 sig figs because we started with the 29.95. That has 4 sig figs. That was our given. And so in the last one, we rounded this to 0.03744. Either way is correct, and either way AP would accept. So now that I have this number, I use that. That is my known. That's the thing that I know everything about. I know what my molarity was of my HCl, and I know how much of it that I use. So this is my known. I'm going to use that number to figure out, I'm trying to get to concentration of KC6H7O2, which is my stock solution. So let's go back to the very first picture. So in this picture, we're saying that in here, I have HCl, and I know that that HCl has a molarity of 1.25. In here, I have my potassium sorbate, my KC6H7O2. I don't know its concentration, but I do know how much of it I had to use because I did this experiment and I found the equivalence point. So I know how much of this I used, but I don't know its concentration. So going back to my little cheat sheet, I balanced the chemical equation. I have now figured out my moles of the known standard solution. Now I'm going to use stoichiometry and find the moles of my unknown solution. So I'm going to just do a basic mole to mole conversion. So 0.0374 or 0.03744, both are acceptable, moles of HCl times. Going back to my balanced equation, my net ionic equation, I can go all the way back to the original that I had, because all these are positive 1 and negatives 1. Everything is a 1 to 1 to 1 to 1. And so this H is the HCl part because we took out the Cl. So it's going to be 1 mole of HCl. That's the reason I like having the original balanced equation and the net ionic, because most of these problems are going to go back to the original equation when we're talking about acids and bases. And so it helps to be able to have that substance. And so then on top, I'm trying to get to KC6H7O2. So again, if I went back to my original equation, I had it written up here. Hopefully you wrote it down too. It was also 1. So 1 mole of KC6H7O2 gives me, well, since it's 1 and 1, then my final substance is just going to be 0.0374 moles, but now it is KC6H7O2. That is my number of moles. This is asking for concentration, so I'm not quite done. Okay, so I'm going to erase up here. And so I am going to put, I'm trying to get to molarity. That is what my concentration is. So I'm going to put 0.0374 moles of KC6H7O2 over my volume, which is in my original equation. It says a student titrates 45 milliliters of the stock solution. This was the stock solution. So I'm going to convert that 45 milliliters. So I'm going to do 45 divided by 1,000 to get it into liters. 45.00 has 4 sig figs, so my volume also has to have 4 sig figs, so it's going to be 0.04500. And then I'm going to divide those out to solve for my molarity. So I'm going to do 0.0374 divided by 0.04500. Be very careful in your calculator. Make sure that you include those leading zeros, or you're going to always be off by one factor. You'll be off by like a power of 10 or 100 or 1,000 because you've left off those zeros. I need 3 sig figs because this one has 4, this one has 3. And so I'm going to round this. Mine comes out to 0.831. Remember, the unit for molarity is just a big M. So this is my final answer. I had to do all this stuff to get there. It's not hard. It's just a lot of steps. So let's look back here because we're going to practice another one. So you have to balance first, figure out the moles of your known, do stoichiometry, convert to moles of unknown, and then use that to solve for, typically it's going to be molarity of your unknown solution. Okay, so let's try another problem where we go through and do all the same stuff with another example. Now in this one, it's already balanced, so that's nice. We don't have to do that part. It said the student was given a task of determining the molarity of an unknown concentration of H2O2. She analyzed a 10 milliliter sample of H2O2 by titrating it with 0.0330 molarity KMnO4, which has a dark purple color. So this one wasn't necessary to use an indicator because the things were colored. The balanced equation is for the reaction is shown above. A total of 10.69 molarity of 0.0330 molarity KMnO4 was required to reach the equivalence point. Letter A, calculate the number of moles of MnO4 -1 that reacted completely with H2O2, and then calculate the concentration of the H2O2 in the solution. So this comes from our AP classroom videos. So something I want you to notice is they used KMnO4, but up here in the equation it just says MnO4. That's because K is one of our SNAP ions and is always soluble. So this is a net ionic equation, and that's why we are not seeing that K. But we mean the same thing as saying this and saying the moles of MnO4, because the MnO4 is the thing that actually participated in the chemical reaction. The K was a spectator. So going back to my cheat sheet, I have to balance a chemical equation first, already done for me in the problem. Now I have to identify the moles of the known standard solution. So the thing that I know is this part of the problem. That's how I'm going to solve for A. So I'm going to work that out here. So I'm going to use the method where I'm using the molarity equation. Remember that molarity is equal to moles over liters. So I'm going to plug in the 0.0330 molarity. I'm solving for my moles. In my liters, I cannot leave it in milliliters. I have to take 10.69 divided by 1,000, and that is going to give me 0.01069 liters. Mathematically, I'm going to multiply those together because I got to isolate my variable. I'm going to multiply both sides by the 0.01069. So I'm going to multiply that times 0.0330. I need 3 sig figs because this has 3 sig figs. This one has 4. And so my final answer for calculating the number of moles is going to be, and you have to be careful again with your leading zeros, or you can change it to scientific notation. So 0.000, and I need 3 sig figs, so 353. And that's going to be moles of MnO4 -1. That's step 2, so balance equation, find the number of moles. If I go back to my cheat sheet, I now have to use stoichiometry to convert to my moles of my unknown. So I'm going to work that out up here, and then I'm going to pull it down here in a minute. So I'm going to have 0.000353 moles of MnO4 negative 1. So then I go back to my balanced equation. I have a 2 in front of the MnO4. My last one I didn't because they were all balanced with a coefficient of 1. So I'm going to put 2 moles of MnO4 negative 1. And I'm trying to get to H2O2. That's my unknown. So I'm getting to moles of this. So I'm going to do 5 moles of hydrogen peroxide, which is H2O2. So then I'm going to take my 0.000353 times 5 divided by 2. Again, to 3 sig figs, this is going to give me 0.000882 moles of H2O2. So the equation was balanced. I figured out my moles of known. I've now figured out my moles of my unknown. Now I've got to do number 4, where I'm going to solve for the molarity. When it says the brackets, that's what I'm trying to get to. So I'm going to work this out down here. So my molarity is going to be equal to 0.000882 moles over, I got to have volume. It doesn't tell me the volume here. I have to go back to my original equation, and AP does this a lot where you have to pull some numbers from that original paragraph. So it says she analyzed a 10 milliliter sample of the H2O2, and so she used the 10 milliliters of it, and so I'm going to have to convert that. So I'm going to do 10 divided by 1,000. 10.0 has 3 sig figs. That's how many my volume has to have. So I'm going to have 0.0100 liters because I need 3 sig figs. So then I'm going to take 0.000882 divided by 0.0100, and my final molarity is going to be 0.0882 molarity of H2O2, which is what I was trying to get to from the beginning of calculate H2O2. But my brain has to know that that means I need to figure out my moles and divide by my volume to get to that molarity or the concentration. So again, these steps are not difficult by themselves. You just have to practice this enough to get it stuck in your head. So we got to balance the equation, figure out our moles of known, do stoichiometry, figure out our moles of unknown, and then solve for whatever it's asking us for, which most of the time is going to be molarity of the unknown. With titrations, you're going to see things called titration curves. We get into this much more in depth when we get to the acid-base chapter. You have to understand some basic information about acids and bases to be able to understand these titration curves and really to be able to understand acids and bases. And so a couple things just as review. You should have seen this already in your previous chemistry class, but the pH range of an acid is going to be from 0 to 7. pH range of a base is from 7 to 14, and a pH that is equal to 7 is what we say is neutral. So technically it's 6.9 and 7.1, but we just know that those are the ranges and 7 is neutral. On these titration curves, your x-axis is usually going to be the volume, your y-axis is the pH. And so on this problem, it says a strong acid with a strong base, so this is still an acid because the pH is below 7. Equivalence point is where we have an equal number of moles. That's what we're working out on for it's where the moles cancel each other. And then this is going to be base because it's above 7. You do need to memorize this list. This is what I was talking about with that problem. So with the problem I went over with the hydrochloric acid back here, you didn't know anything about hydrochloric acid at that point, unless your previous chemistry class had you memorize that. And so you have to memorize what the strong acids are, and then everything else is just a weak acid. That's the way AP simplifies it down. So our strong acids, 3 of them are what we call binary acids. They come from the periodic table. They're hydrogen bonded with one other element. These are all halogens. So HCl, HBr, HI. And then you have to memorize these other ones. You have to know HNO3, HClO4, H2SO4. All of these are strong acids. Anything else that says that it's an acid that is not these is going to um, be a weak acid. So why does that matter? Because strong acids are always going to be aqueous. They're going to separate. The ions completely separate. That's what we saw with HCl. It's going to separate in pH plus and Cl minus. They're going to separate out completely. Weak acids are going to be liquids. They're going to stay together. Some are going to separate, but most of them are going to stay together. The attractive forces holding them together is very strong, and so they don't break apart, and so they're going to stay as a liquid. What makes an acid is the production of hydrogen when we put it into water. So strong acids make a whole bunch of hydrogens, making them strong. Weak acids don't make many hydrogens, making them weak. Bases, again, AP simplifies this. You're going to see some different rules when you get into college level, but AP says that any metal that is bonded with hydroxide, any metal from group 1 or group 2, is going to be considered a strong base. So group 1 metals would look like this, NaOH. Remember, OH is a polyatomic ion. That's what makes a base, is the production of OH. And so NaOH is going to be a strong base. Your group 2 bases are going to look like this, because sodium is a positive 1 charge, barium is a positive 2, and so it's going to be barium hydroxide, again the OH, but it will have a subscript out here. All these are considered to be strong. Any of those metals from group 1 or group 2, those are going to be considered to be strong bases. And that is the end of today's lesson. You definitely want to get comfortable with this, because titrations are a big part of acids and bases chapter, and also we see them a lot with those oxidation and reduction reactions.